Okay, so today we'll be doing a special type of functional equations which have a number theoretic flavor. So they'll be from either from naturals to naturals or from integers to integers. And before we go into this, I would like to cover some basics of functional equations in general and also some special ideas which we'll be using in the N to N or Z to Z FEs. So first of all, some basic properties of functional equations are okay. First of all, what's a functional equation? It's a function, say we map it from some set of numbers to some other set of numbers. So for example, it could be from naturals to naturals. So this function takes in some input, say f of 1, and it gives out some output. So this would mean that f of 1 is equal to 2. So the set of integers it maps from is called the domain, and the set of numbers, and the set of numbers it maps to is called the range. The set of numbers it maps to is called the codomain, and the specific numbers it goes to is called the range. So for example, suppose we have f of n is equal to n plus 1. So the codomain is the naturals, but the range is actually not the entire set of the naturals, because we'll have, say, f of 1 is equal to 2, f of 2 is equal to 3, and so on. But nothing goes to 1. So there is no x such that f of x is equal to 1. So therefore, the codomain here is all the naturals, but the range is just everything from 2 onwards. This is just like formal definitions. Anyway, some properties of functions that you can have are, the first one is injectivity. So a function is injective if for any f of a equals f of b, you always have a equals b. So essentially, you don't have two different inputs mapped to the same output. This does not happen. And this property is called injectivity, and it's in general a useful thing to prove. So whenever you have some function equation, this is something you can try to prove. The second property is surjectivity. So this means that the codomain that we defined here is equal to the range. So everything, for every element of the codomain, there is something mapping to it. Yeah, injectivity means each input has a unique output. So no two inputs have the same output. Yeah, feel free to interrupt me or type in chat or unmute if you have any questions. Okay. So for surjectivity, suppose I have a function from, say, naturals to naturals. That means that for every natural, there is something that maps to it. These are just some properties which could be useful to prove when you're doing problems. That's why I'm going over these. Okay, so if a function is both injective, um, okay, the use of functional equations is like it is a type of problem that shows up sometimes. So we'll go through examples and then you'll understand better. Okay, so now if a function is both injective and surjective, then we say that it is bijective. So that means that every element in the range has something going to it, and that is unique. Every element in the code. So I hope all this terminology is clear. Um, okay, for surjective is, so you have a set of numbers to which the function maps, right? It could be reals to reals. So that would be denoted as f of like this. So for example, if you're looking at reals, if a function is surjective, that means for any real y, we have some x such that f of x is equal to y. So you can always find something mapping to whatever you want in your codomain. So the y is in here. Okay, how is injectivity unique? That's just how it's defined. So basically, if you have two different numbers mapping to the same number, that's a contradiction to injectivity. That's why if you have f of a is equal to f of b, then these must actually be the same number. So no two different inputs can map to the same output. Okay. I hope this is clear to everyone. Yes, subjectivity may not be unique. Injectivity and subjectivity are not the same thing. So for subjectivity, you can have multiple things mapping to every value in the codomain. Yeah. So now moving on to number theory specifically. Um, okay, so there are a few things I want to go over before we go into problems. The first thing is Euclid's algorithm. I think this has been covered before, but I'll just go through it again. So this is just a process by which you look at divisibility of numbers. So for example, if I want to find the remainder when, say, 37 is divided by 5. So what I do is I repeatedly subtract 5 from 37. So we can subtract it 7 times. So we get 37, then 32, and so on till 2. And since I've subtracted the 7 times, the quotient is 7 and the remainder is 2. This is what you do in school, right? So how we'll be using this here is we'll be using this with actual variables. So for example, if I have something like, this is just a random example, but if I say AB plus B divides B square, what I can do is I can subtract multiples of, okay, let's say this is, okay, B square plus A square, for example. So what I can do is I can subtract multiples of the divisor from the thing I'm dividing. Because, for example, we also know that AB plus B divides um, AB squared plus B squared, right? You're just multiplying it by B. So if it divides both of these things, I can just subtract them and it must divide the result as well. So if I subtract the first one from the second one, then I get AB plus B divides AB square minus A square. So this is like some new information which I get. And this is a very useful thing, not just in number theoretic functional equations, but also generally like for number theory problems with divisibilities in them. So sometimes what happens is I can keep on subtracting things in some way, and finally I get something very small on the um, right side. So then there can be two cases. So you have in general that if say C divides D, then either the absolute value of C is at most the absolute value of D, or D is 0. Yeah, you can in general reduce the powers of variables by doing this. In fact, we'll be doing that in one of our problems. But yes, so the whole point of doing this process is when you get something like this, you have this equality. And sometimes this is like directly a contradiction, which means you get D is 0. So that is why this method is powerful. Yes, so that is mostly what I wanted to do before going into the problems. Okay, first we'll do a small exercise, which is not exactly a functional equation, but it will be useful. So what I want you to prove is, so suppose A and B are natural numbers and they're coprime. So their GCD is 1. I want to prove that a to the power d minus b to the power d divides a to the power n minus b to the power n if and only if d is a divisor of n. So you can try this for some time, and if someone has a proof, you can go ahead. If you have a proof for either direction, you can do that, and we'll start with whichever you want. So yeah, you can try this.
I can prove the thing.
Okay, sure. Go ahead.
Okay, so for the first direction, suppose that d divides n,
Okay.
then we write n as some d times k,
Okay.
and then we write a raised to d minus b raised to d divides a raised to dk minus b raised to dk.
So this is what we want to prove. Okay.
And then we can take a raised to d and b raised to d as some variables and then apply factor theorem to it.
Sure. So you can take this as some x and this as some y. So what you want to show is x minus y divides x raised to k minus y raised to k. And do you have a proof of this? I know this is sort of well known, but I'd still like to prove it.
Yeah, you can assume x raised to k minus y raised to k as some polynomial in x, and then you put x equal to y and by factor theorem you get that this is a factor.
Ah, okay, sure. That works. You can also prove it by induction. So something else you can do is, wait, someone had a question. Yeah, sure. So one proof is the polynomial one, like directly showing that this polynomial divides this polynomial. But a more number theoretic proof you can do is you can just multiply this by, so you know x minus y divides x raised to k minus y times x raised to k minus 1. So subtracting, what you want to show becomes y times x raised to k minus 1 minus y raised to k. Now since x and y are coprime, you can, like, this extra factor of y does not really contribute. So this becomes equivalent to x raised to k minus 1 minus y raised to k minus 1. And you can keep reducing the power, and by induction, you're done. Okay, so I hope both the proofs were clear
Like,
to
may
everyone.
I?
Yeah, sure.
So in that step, like x minus y divides x to the k minus y to the k. I mean,
Yeah,
can we use like mod x minus y?
yeah, sure.
Thank you.
Yeah, so you can also say x is congruent to y mod x minus y, and then you can just raise both sides to k. Yeah, this also works. Okay. Now can someone prove the other direction? And you can use the first direction to prove the second. That might make it easier.
Assume that d does not divide n, then you can write n as n d plus r, and then we show that r is 0.
Yeah. So for the sake of contradiction, you can assume, suppose ad minus a raised to d minus b raised to d divides this. What we know is it also divides this by what we proved before. So can we use this to prove a contradiction?
Okay, so like, doesn't it become the same form that a to the d minus b to the d divides a to the d raised to the power of m? Then same thing like minus raised to the power of n.
Yeah, that's what we used to prove this part, but we need to disprove this. So this is point where the Euclidean algorithm comes in useful. So the point is, if we can reduce this to something like a raised to d minus b raised to d divides a raised to r minus b raised to r, this would be a size contradiction because d is greater than r. So if we can get this, then we'd be done. And can we somehow do this using the division algorithm? Actually, I don't think you need this. Yeah, I think you can directly do this.
Keep on subtracting the actual divisibility that we have, and then the exponent should follow the algorithm, right?
Yes, that is the idea. So the idea is to sort of replicate the algorithm for the exponents, as he said. So what is the most direct thing to subtract? We want to somehow get rid of this term. So in order to obtain that term, we have to multiply a raised to d times a raised to m minus 1d plus r, and similar, so we multiply b raised to d also by this. So we know that this divides this. So this is what we want. So now when we subtract, this and this cancel. So what you get is a raised to d minus b raised to d divides uh, b raised to d times this. And now you can get rid of the extra b factor because they're coprime, so it doesn't contribute. So I'm just using that GCD of, I'm just using this fact. So what I did here is I got from this form to this form. So the number of times d comes in this number, it decreases by 1. So essentially we are mimicking the division algorithm again. We're dividing md plus r by d. And as you can see, we can keep on reducing this m by subtracting d. So eventually what you would get is when m becomes 0, you get what we wanted. A raised to d minus b raised to d divides this. And now that means that the size is less than the size of this. But this is a contradiction because d is greater than r, so contradiction. So is everyone able to follow? Are there any questions?
Is it necessary for A and B to be coprime? Because can't we just remove the common stuff out?
The issue here is the b raised to d is still over here and you're getting rid of that.
No, like if suppose GCD is not 1, then because the thing that we're dividing by, since its
Yeah.
degree is smaller, can't we just cancel that out in the divisibility?
Okay, yeah, that is true. We can do that. So yeah, you don't need this condition. So I guess if you have, say, mm, C time, okay. Suppose you have some C is equal to A times G and D is equal to B times G, then what you want to prove is so yes, you can just cancel out the common part, you're right. So you don't need the coprime.
No, wait, but the exponent of G is different, right?
Yes, but like a smaller exponent dividing a larger exponent is not really the problem. So that's why that part doesn't really matter.
But then in the right hand side of the division, G still remains, right? I mean, G to the power n minus D is still there. We have to. Okay, no, no, yeah, sorry. It's fine.
Okay.
It's fine.
If you have any questions, just ask. It's fine. Okay, so that was the main stuff I wanted to cover. Now we can directly move on to problems. So this is the first problem. You can try it, and any ideas you have, you can feel free to speak or type in chat, preferably speak. In case you've seen this problem, you can let me know. I'll give you something else to try. The function is from all integers to themselves. So not just natural. Yes, so identity does work. Yes, you're right. So f of x equal to x raised to k also works, where k divides n. And this is because of the thing we just proved. So the condition would be this. And we know this is true because we just proved it. Mhm.
I got f of p equal to some power of p.
Okay, that's great. How did you get that?
So since you have a difference that is dividing, we can just assume f of 0 to be 0 by translation.
Yes. Okay, so
And then you set y equal to 0 and x equal to some prime.
yes, we can shift f by a constant. So in fact, this form should work. So we can assume f of 0 is 0 because whatever f of 0 is, we can shift it to be 0. So now we get, so in general, for functional equations involving like number theoretic um, domains, a nice thing to do is look at primes. So if you just directly plug in a prime, so here you get that f of b must be some prime power. So let's call it b to the m.
It's saying that for any value of f of 0, we can just scale those functions or can add into it. So we'll get
Yes.
functions. Okay.
Yeah.
So you have to specify that, right?
Yes, you have to say that you can shift f by a constant. So try plugging in some other values. Uh, um, okay, someone asked what happened so far. So far we just went through some general properties of functional functions, injectivity, surjectivity, and bijectivity. And we also discussed Euclid's algorithm. That's mostly what we did. And we also proved that a raised to d minus b raised to d divides a raised to n minus b raised to n if and only if d is a divisor of n. And we'll be using that in this problem that we're trying.
So, like in that f of p is equal to b raised to the m, is it necessary that m divides n?
It should be like that's what we believe, but we haven't shown this yet. So trying to show this would be a good next step.
Just set x and y to both be primes.
Okay. Yes.
And then the
So
result would
use
follow
it.
from our previous thing.
But we don't know that this exponent is the same, right? So you can have f of q is q raised to l. So that
Yeah,
might not
so
directly work.
We can say that f of 1 is equal to 1 because of our scaling thing. And
Yes.
that will say that f of p minus 1 should divide p to the power n minus 1, which means p to the power m minus 1 has to divide p to the power n minus 1, which means n divides n.
Yes. Perfect. Okay. So first of all, putting in 1 and 0 gives f of 1 divides 1. Now, no, so f of 1 must be 1 or minus 1. But again, if you note that flipping the signs of everything in f also does not change anything. So we can also flip the sign of f. So therefore, we can assume f of 1 is equal to 1. So now, in order to prove what we wanted, like to prove m divides n, we plug in p and 1. And this gives us p to the m minus 1 divides p to the n minus 1. So you can consider that to be an m here and an n here. And by the thing we proved before, we get that m divides n. And in fact, even if you did not have that in mind, seeing this here, the next thing you do should be trying to subtract powers of p from this side and trying to reduce it to something. And eventually you'll get that m must divide n. So, okay, but you still don't know that every prime goes to the same power. So you can try to do something about that now or try something for a general x.
In the question, is it given that f of n is constant, sorry, f of x is constant for a specific n, or can it vary for each n?
Yeah, so for different values of n, the function would be different.
Okay.
Okay, so now since you have a nice form for a prime, the next thing you can try to do is, so there's mostly two options. One is try to show all primes go to the same power.
Showing that all the
Or
primes go to the same power will essentially prove a statement here. And that's not
it
right.
still have to prove for non-primes.
Mm, if they all have the same powers, we can just write it as, we can write each composite as product of prime powers. So,
But you don't know
yeah,
that it's like multiplicative, right? You don't know that f of
yeah,
x,
yeah,
y.
sorry, yeah.
Yeah, it's okay. Yeah, this other option is to do something with general x because you have some information now, so maybe it might be enough to directly finish. Should try plugging a prime and like a general value for x into the function. Try to see what you get.
I think I have something.
Okay.
So we put x equal to p and just keep y as it is.
Mm-hmm.
And then you get p raised to m minus f of y divides p raised to n minus y raised to n.
Yes.
And then we keep on subtracting p raised to m minus f of y till the p raised to n disappears.
Yeah, exactly. So we
And
can
then
write this as p
because
raised. Yeah, go on.
the right hand side becomes fixed, we can just take p to be some very large prime and conclude it to be zero.
Yeah, yeah, perfect. So what you can do here is you can multiply the left hand side by p raised to k minus 1m. So then you subtract this. So then what you get is p raised to m minus f of y divides this. So this is just an attempt to get rid of this large power of p. So now the point is you can keep doing this. So again, now we can still try to get rid of this, right? So if you subtract, um, sorry, yeah, you can multiply the left hand side by f of y times p raised to k minus k minus 2. And again, if you subtract, you will get so essentially the right hand side is of the form f raised to y raised to some power times p raised to k minus I times m minus this term. And this is what happens when you keep doing this process of essentially trying to get rid of this term, the left term. So finally, when I becomes equal to k, then what you get is the left hand side divides f of y times k raised to k minus y raised to km, which is just y raised to m. So now the thing is, p can be any prime. Like you can take p to be any very large prime. And um, and you know that the size of this must be at most the size of this. So this is not possible when you take p to be very large, which means the RHS must be equal to 0, which means f of y raised to k is equal to y raised to km, which means f of y is equal to y raised to m. So this means that upon shifting and flipping the sign, f of y is y raised to m. So it's actually plus or minus y raised to m plus some constant. Because we have shifted it and we have flipped the sign, so this is the general form. So the main idea after getting that prime goes to a prime power which divides n, the main idea after that is you just plug in a prime and a random value, and then you keep on applying this subtracting idea which we looked at earlier. You keep on applying that on the right hand side in order to get rid of the term containing the power of p. So finally, when that power of p vanishes, you get something on the right side which is independent of p. And then you have this issue. So I hope this, yeah, so all the functions we get are y raised to, so f of y goes to y raised to m plus some constant, and you can make it negative also. And the reason is because we got this after shifting by some constant. So if you shift back, it goes to this form. And you can flip the sign also. So does anyone have any questions? I think the main tricky part was the subtracting idea and getting this form. So if anyone has any questions about those, please ask right now, or else we can go to the next problem. Okay, so I'll assume it's clear. This is the next problem. You can try this now. Well, when you write p of something, comma something, that means that you're substituting that. So, for example, here, if I want to substitute, say, m is equal to 1 and n is equal to 2, instead of writing that, I can just write p of 1 comma 2. It's just a short form of writing this. So if I
Okay, so
say,
let's start with 0 comma 10, right?
um, this is from naturals to natural, so you can't have
Alright, we
0.
can put.
Yeah, to answer someone's question, the notation is standard, but it's good to mention at the start that if P, let P of Mn be the assertion, so they know what you're talking about when you write P of something, comma something.
Would it be better to look at this like a divisibility? Like m plus n divides the RHS?
Yeah, that is a good way of looking at it. But yeah, the other part, this is still important as well.
We can just put m equal to n.
Sure, yes.
It's so
So you get this.
maybe f of 2n squared.
Yes, 2n squared. So you get f of n is equal to f of 2n squared, and this is actually useful, so keep this in mind.
So with this, we know that f of 1 is equal to f of 2. And in the original equation, you can put m and x 1, 2, then figure out the value of f of 1 and f of 2.
F of
I
1
mean,
is
that won't give the value, but it would give us f of 5 in terms of f of 1 and f of 2.
okay. So we get um 3 f. Are you saying we just put in 1 and 2?
Yeah.
Yeah, sure.
So that gives us f of 5 is equal to f of 1.
Yes. Yeah, because these are equal. This gives us f of 5 is equal to f of 1. So based on what you're getting, can you guess what the function could be?
Constant function.
Yeah, it looks like it has to be constant. This is what we're claiming.
So we can induct this and maybe go on having
Mm,
infinite.
You could, but can you prove that you attain all the values? That might be tricky. Yeah, I think someone had asked, so this does mean that it satisfies for all integers, m and n, all positive integers.
I think you can also get f of m squared equal to f of m.
Okay,
So
how
use
are you
p
doing
of m
this?
comma m, p of m squared comma m squared comma m squared.
Like this?
Yeah,
Okay, so this gives 2m squared times.
wait, I might be messing up here. Yeah, no,
See what we get.
that doesn't work.
That's fine. So the main thing that this kind of substitution gives us is that f of n is equal to f of something which is of the order of n squared. So you can keep on continuing this process and you can get f of n is equal to something is equal to f of something very large. You can get this to be as large as you want. So this can be useful. So you have some sort of control over size. And as someone mentioned before, you can treat this as a divisibility as well. So one idea is divisibility. So when you both have size and divisibility, you can try to get like some kind of contradiction. Yes, so if you want to treat this as a divisibility, there's two things you can do. You can look at it this way or the other way. So try to play with both of these forms. Try plugging in things as well and using some of the ideas we saw before. So the divisibility part, it's just saying that we have the product of two things is equal to something else. So that's the same as saying each of these divides the right hand side. So we can try to use those separately. Just using the fact that m plus n divides this, maybe it gives us something useful. So seeing it as a divisibility and not just an equality might help.
Okay, yeah, sure.
Okay, let's try plugging in some values. So the first one thing we could do that we did before is try subtracting something like um we can write m plus n divides f f of times n, and if we subtract this from the previous thing, you subtract these two, then you get m plus n divides n times f of n minus n times f of m. So here we can choose n to be any value. So what would be a nice value to choose so that this becomes something nice, this equation?
n equal to 1.
Yeah, n equal to 1 would make it very nice, right? Because you have m plus 1 divides this, which is quite neat.
Right, and because the function cycles back, you can take n to be very large, right?
Yeah, you know that f of m can be equal to f of something very large. So you can fix this value. So let's take some very large m, let's call it n. So let's say f of n is equal to f of m, and you can have n very large. So then you have n plus 1 divides f of 1 minus f of n, which is equal to f of 1 minus f of m. So if you just take n larger than f of m, which you can do, you can just you can get n as large as you want. You can't take any n, but you can get some n because you have f of m is equal to f of 2m squared. This is equal to f of 2 times 4m raised to 4 and so on. You can make this very large, right? So just make it that large and then you have this relation, but this must be a contradiction, right? Because this is too small, which means it must be 0. So f of m equal to f of 1 for all m, which means the function is just a constant and any constant works. Did everyone follow? So there were mostly two parts to this. One part was the size part, and one part was the divisibility. So that was the main idea of this problem. First, we get that f of n can be equal to f of something arbitrarily large. And then we use the divisibility to manipulate and get to this point at which size just finishes. So if anyone has any questions, feel free to ask. Otherwise, we can move on.
Don't we know that f of n is already the constant because we get it from 1, right? 1 to n square, 2 into 1 square, and so on.
No, but m need not be something you get in that sequence, right? Like from the one sequence, you get f of 1 is equal to f of 2, then you get this is equal to f of 8, then f of 128 or something like that. But this does not cover all integers.
Okay. But if the right hand side n plus 1 divides f of 1 minus f of n, so what is the problem if f of n, f of 1 minus f of n is negative?
The problem is the size. So we're looking at the absolute value. So remember we said that if c divides d, then either this is true or d is 0. So like this is the same as saying n plus 1 divides f of n minus f of 1. There's no difference. The sign does not really matter.
Okay, I got it. Thank you.
Okay. Someone asked how I took this n substitution. So what we want as a contradiction is we want the left-hand side to become too large. So we know that we can get f of m is equal to f of something very big. So if we put in that value as m, you get something very big on the left side, and that is your capital N. But the right side is just the same right side that you have over here. So it's this substitution from which you just put in n, a very large n. But this value is still the same. Like the f of n is still equal to f of n. You pick such an n that's very large, but these values are the same. And you know you can do that because of this thing you got before. Does that make sense?
Yeah, sure. Thank you.
Okay. Okay. You can try the next problem now.
Positive integers are just integers, right?
Yes, so positive integers just means the same as n to n. the same thing. Here, yes, identity will work. Mm, Constant. Okay, if f was a constant, then you'd have f of okay. I mean, constant could still work. Like if it was a constant, then it had to be like c equals to c factorial, which implies c is 1 or 2. So all f equal to 1 or all f equal to 2 would also work. Yeah. Try to put in some small values, see if you can figure out what f has to be for a few values. And also something else you can do is you have two different conditions. You can try combining them. M raised to n f of, so what do you mean? Like, do you mean f of m is m raised to n? Because I don't think that would satisfy the factorial. Do you mean like this? I don't think this would hold. Like you can try looking at the powers of exponents, and this won't always hold. But yeah, it's a good guess.
Putting n
Yeah,
equal
yeah, go ahead. What do you say? Okay, if you put n equal to 1, you get f of 1 is equal to f of 1 factorial. And the only numbers which satisfy like being equal to their own factorial at 1 or 2. So f of 1 is equal to 1 or 2. And similarly, you get the same thing for f of 2. So now you have like 4 different cases. So I would say first try to eliminate f of 2 is equal to 1. Also, something else I'd mentioned is trying to combine both the conditions. So we have that m minus n divides f of m minus f of n. So if we put the factorial thing into this, then what do we get?
m equal to 2, n equal to 1.
No, I meant putting this condition. Put m and n as some factorials.
You get that factorial.
Yeah, we can take this out. And in particular, are there some nice related values we could use for m and n? For example, if we put m and n as consecutive values, in n plus 1 factorial minus n factorial, and this, is equal to n times n factorial. This divides this. So what happens if f of 2 is 1 and you put that into this? So you get f of 3 factorial is congruent to 1 mod 4, which means it's odd. But a factorial can't be odd unless it's 1 factorial, right? So then you get f of 3 is, this is 1 factorial, which means f of 3 is 1. So, okay, the eliminator, like there is still a solution, right? So in general, if you get f of n is equal to f of n factorial is equal to 1, can we use induction to prove this for f of n plus 1 factorial for n greater than or equal to 2, because this doesn't work if n is 1.
It's the same process that we do right now.
Yes, yes. So the point is, over here you get something divisible by 2. If both of these numbers are greater than 1, here this is like 0 mod 2. But then on the RHS, you'd get basically f of n plus 1 factorial congruent to 1 mod 2. And this gives that this is also 1. So basically, if f of 2 is 1, then everything after that is 1. And that is one solution. And I think in that case, f of 1 has to be 1. Yes, because otherwise you can have something like 3 minus 1 divides f of 3 minus f of 1. But if f of 1 is 2 and this is 1, then you get 2 divides minus 1. That's a contradiction. So if f of 2 is 1, then that means that f is just constant. And you have two remaining cases. So remaining cases, 1 is 1, f of 2 is 2, and f of 1 is 2, and f of 2 is 2. So till here, is everyone clear what we did? We just proved that by induction. If value goes, then the next one. So using this form. So now we can try to resolve these two cases. So something that worked before was inducting on n to prove that everything is equal to 1. So here in this case, what we'd like to prove is that f of n is equal to n, right? So maybe induction could also help us here. Maybe try using the same identities that we got. And we can look at this case at the end. It shouldn't be too hard. Okay, so since we're sort of running out of time, I'll try to go a little faster. So what we're trying to prove is that given f of n is equal to n, we're trying to prove that f of n plus 1 is equal to n plus 1. So suppose we do this. In this first case, we'll get identity. In the second case, we'll get something slightly weird. But the point is, if we do this in the second case, you'll have f of 3 is equal to 3, and again you can have a contradiction with f of 1 and f of 3. You'll have 3 minus 1 divides 3 minus 2, which is contradiction. So this is what it actually suffices to prove. And then we would be done. And this induction would be starting from. So how would we go about this? Suppose we have proven, like assume we have proven for n. Then we have n times n factorial divides f of n plus 1 factorial minus n factorial. We get that from this identity. Now, this is essentially saying that f of n plus 1 is congruent to n factorial mod this. And we also know from the identity at the beginning that okay, actually let's just work with this for now. So now the point is this is a factorial. So if this becomes large enough, then like a lot of things will divide it. So it'll just become 0 mod this part. So more precisely, if f of n plus 1 is at least 2n, then its factorial will be 2n times a bunch of stuff and then times n factorial. So n times n factorial will divide it. And that would be a contradiction because this is not 0 mod n times n factorial. So you have to have f of n plus 1 is at most is less than 2n. This is one thing. So how can you finish from here?
I think this implies that f of n plus 1 equals n.
And why is that?
Because f of n plus 1 is less than 2n, and also n factorial divides f of n plus 1 factorial minus n factorial, which, oh, okay, okay, maybe.
Yeah, but like if f of n plus 1 would equal f of n, wouldn't it apply that 2 equals to 1? Like that is like up.
We're trying to show f of n plus 1 is equal to n plus 1. So that would be fine, right? Since f has integer codomain, why would that imply f of n plus 1 is equal to n? Okay, let's also try using the initial identity. Maybe this could help. So, like we know a lot of values, right? You can assume that everything is true from f of 2 onwards. You can assume f of 2 is 2 and all the way till f of n. So, putting in n plus 1 and say 2, you'd get n plus 1 minus 2 divides f of n plus 1 minus 2. So n minus 1 divides this. And this would give you that f of n plus 1 is congruent to 2 mod n minus 1. So it's either equal to 2 or it's so this basically splits into two cases. Like either you have everything becoming equal to 2 or everything equal to itself. And you can just figure out those two cases. So yeah. Yeah, so this would essentially depend on f of 3 as well. So if f of 3 is also equal to 2, then you get one more congruence. Right, so if f of 3 is equal to 2 or f of 3 is equal to 3, from here you get one more congruence, and that basically gives you the value of f of n plus 1. Because you have two congruences and you can use, you can combine them, and you also know that it's less than 2n. So that just gives you one of the two cases. I'll leave you to work out the details yourself. It's not that complicated. So I hope you understood what happened in this problem. So essentially, we combined the two identities that we had, and then we used some small cases to start off this induction process. Okay, so that will be all for today's class. I'll stop the recording.